Hello. Today's lecture will be on balance and postural control. By the end of this lecture, you should be able to describe the major terms in balance and postural control, identify the difference between static and dynamic balance, and describe the major balance systems that we use in everyday life. Let's start by talking about the terminology we need to describe balance and postural control. First, we can talk about our body's center of mass. The center of mass is the point that is at the geometric center of a distributed body mass. We can think about this as the individual components of all of the centers of mass of each of our body segments. So the masses of our foot, the mass of our hands, the mass of our head, and where those are relative to each other. If we add all those up, we can find a point in space that is the location of our center of mass. Generally speaking, our body's center of mass is about 20 millimeters in front of our second lumbar vertebrae, meaning it's pretty close to where our belly button is. The second term we need to know is our ground reaction force. The ground reaction force is the force exerted by the ground onto our body. This is the force that we feel when we're standing on an object. In this example, this person is feeling the ground reaction force on their hands. Each body part that stands onto or that touches a surface is going to feel this reaction force. We can sum these reaction forces to get some kind of net ground reaction force, shown here in white. The center of pressure is the location of this ground reaction force. Our base of support is defined by the maximum distance or the area where that center of pressure can be located. In this case, it would be the edges of where this person's hands are. Usually, the base of support is defined by the outermost edges of whatever surfaces or whatever body part is touching the ground. Ultimately, what keeps us balanced is keeping our center of mass and our center of pressure largely aligned. Balance is most generally the ability to resist gravity and avoid falling. Most of the time, balance involves maintaining the center of mass directly within the base of support. This is largely true in what we might call quasi-static conditions. This would be when a person is moving slow enough to be considered in individual static or not moving positions. Here we can see that this individual's center of mass, shown with the circle with the X through it, is the sum of the individual positions of each body position or body part center of mass, shown here with the red circles. Each joint is indicated with a solid white circle. You'll notice that the center of pressure for this individual has to stay within the feet, and stay within the position of their hands. And the base of support is defined by the red dashed lines, showing the most forward and backward positions of the hands. This person is able to maintain balance because their center of mass never leaves their base of support. If a requirement for balance is that our center of mass is within our base of support, do you think this person is falling or are they stable? Would your answer change if you saw this image? It's important to note that there's a difference between static balance and dynamic balance. Both of these are important for our balance control system. Static is the condition of being not moving or moving very, very slowly. In dynamic conditions, our base of support and center of mass can have a different relationship. When we think about balance, we often think about our static balance, or the ability to maintain a desired body position. When we think about dynamic balance, we think about the ability to move in a controlled way. Both of these things are important to our everyday balance. So now let's talk about what systems influence balance control. There are 6 different systems that we think about within a balance framework. These systems include biomechanical constraints, limits of stability, postural responses, sensory orientation, control of dynamics, and cognitive control. Biomechanical constraints are things that might influence how we interact with our environment. These include things such as the size of our base of support, the number of degrees of freedom that we might have. For instance, if we have a cast going through multiple joints, and how strong our muscles are. In other words, how much force can we actually apply? One of the most common biomechanical constraints is the size of our base of support. This can be constrained either by walking on narrow ledges, for instance, balance beams, which constrains where our base of support can be placed, or even the size of our feet. As we saw in the earlier videos, our base of support is essential, or the size of our base of support is essential to maintaining our center of mass. And our center of mass must stay within that in quasi-static conditions. A second system of balance is our limit of stability. This includes things both in our perception of our limit of stability, but also in how stiff or vertical our verticality we can be. Typically, we can think about our limits of stability as being a cone. This is because we generally resemble an inverted pendulum, where our center of mass can be positioned somewhere within this cone of stability. So we can basically oscillate around this area where we are going to be stable. In most cases, this cone of stability is about 8 degrees in the forward direction and 4 degrees in the backward direction. Another system of balance is our postural responses. We can think of postural responses as both being reactive and anticipatory. These include things such as movement strategies. You can think about this as how you would respond to a loss of balance, or how you would respond to a swaying or moving platform. There are 3 different movement strategies. On the left here is illustrated an ankle strategy. This person is moving about their ankle and they're swaying back and forth. On the right is called a hip strategy. You can see that this person is oscillating about their hip. And on the in the center is the hip strategy. On the far right, you see a stepping strategy. In this case, someone actually took a step to maintain balance. These movement strategies change based on our demands. An ankle strategy and a hip strategy are what we call in-place responses. If we don't want to move or can't move our feet, we might choose an ankle or a hip strategy. However, we can also change the base of our support. If you recall, our base of support needs to contain where the location of the center of mass. So if we take a step, we can increase the size of our base of support. This type of stepping strategy, and in some cases a reaching strategy, can be very effective at recovering our balance. Our fourth system of balance is called sensory orientation. And this involves how we use our sensory information to maintain balance. We have 3 main sensory systems that we use for balance. We use our vestibular system, which is our inner ear, to give us a representation of ourself with respect to our gravitational field. That is, we use our vestibular system to tell us how we are oriented relative to Earth. We use our visual sensory information to tell us how we are oriented relative to surrounding objects that we might see. And we use our somatosensory system, which are sensors that are located within our joints and our muscles, to tell us how our body segments are oriented with respect to themselves or objects that we are in contact with. We use all of these sensory systems at once, but we don't weight them all the same. So if we are standing on a really hard surface in a very well-lit room, we are going to use the predominant sensory system of our somatosensory information. We'll weight these differently, depending on different conditions and different pathologies that might exist across people. For instance, if we're standing on an unstable surface, we might depend a lot more on our vestibular sensory system. If you are walking in a dark room, you're going to rely a little bit more on your somatosensory system and vestibular system, and you're going to rely a little bit less on your visual sensory system because you can't make out objects because of the lighting conditions. This ability to re-weight our sensory information is very critical to walking in complex environments where situational cues and environments change. Our fifth system of balance is the control of dynamics. We mentioned early about how there's a difference between static balance and dynamic balance. When we look at dynamic balance, we often are talking about gait or walking. When we walk, we don't have a perfectly straight line. Instead, we oscillate back and forth. If you look at a sagittal plane view, which is a view from the side, our center of mass is going to oscillate up and down. And if you look at a horizontal view, this is a view from the top, our center of mass is going to oscillate to the right and to the left as someone walks. This means that the control of balance during gait requires complex control of our moving center of mass. To illustrate this, we can look at how that center of mass, shown here in the white and black circle, moves as someone walks. And you can see that it falls forward with each step, and it falls a little bit to the left or right. And as someone continues to walk, it's going to continue to oscillate in these sinusoidal patterns. The way our center of mass moves is based on the pendulum or the length of our leg. As you can see, the center of mass moved along an arc that was connected by the leg that was in contact with the ground. We regulate the control of our center of mass largely by where we place that foot, which controls how that center of mass can move along that arc. The last system of balance is our cognitive control. You can think about walking or standing and either carrying a conversation or texting or trying to pay attention to this lecture. All of this requires cognitive resources. We can think about cognitive resources as how hard it might be. And any of these tasks will create some type of challenge to our cognition. The most common example is what we might call a dual task effect. A dual task effect is something that occurs when you're performing two tasks at the same time, such as walking and talking. When we look at walking speed, we see that people slow down when they both walk and talk at the same time compared to when they just walk. Further, this appears to be worse in people who might have impaired cognition or impaired gait. Both of those conditions can cause a dual task effect that is worse in some populations than others. For instance, older adults often have more severe dual task effects than young adults. So by now, you should be able to describe the 6 systems of balance and talk about why each one might be important to our balance control. Thank you.